everyone, we're so happy that you were able to join us at the Lamont Doherty Earth Observatory Open House. My name is Laurel DiSera, and I'm a researcher at the International Research Institute for Climate and Society, which is part of the Earth Institute at Columbia University. Today I'm going to be talking to you and discussing climate research methods and climate communication. So let's get started. First off, what makes good research? What is good research? What is research? Where can we do research? You can see here, Snoopy is doing research in a chemistry lab, but research can be done in biology, in physics, sociology, psychology, musicology, in a variety of areas, including climate science, and climatology. And that's what we're going to focus on today. But what makes good research? Think about that. How do we start good research? Maybe that's where we should start. So what are some initial questions we can ask? Maybe the first that I start with when doing research is, has this research been done in the past? Has my topic been researched before? If so, what can I learn from it, or how can I improve on what's already been done? I don't need to reinvent the wheel by making a whole new methodology if there's already pre-existing literature with existing methodology. Of course, if you're going to use somebody's methodology, you need to give them credit, but it can be a good way to continue and further research. And if the research hasn't been done in the past, then it's your project. You are creating a new methodology, which is very exciting. Secondly, I like to ask, who can benefit from my research? What kind of impact am I going to be making on society? And thirdly, what need does this research fill? Who can it benefit, but also does it have a need that it's fulfilling? And that's very important. So after we have these kind of initial and basic questions, we need to incorporate them into the scientific method. What does good research methodology look like? Well, from when we were in probably elementary school, we started learning about the scientific method. We have our question, something we're curious about, which we kind of discussed in the last slide, and then forming our hypothesis, then based off of our hypothesis, creating an experiment, collecting our data from the experiment, analyzing the data to draw conclusions, and finally reporting on what our results are and our conclusions have found. But how can we improve on this? How can we improve on the scientific method? My first suggestion for you, all of you scientists, is to make your methods robust by considering all factors and viewpoints. Now, sometimes this takes a little bit of elbow grease, a little bit of work to get done. But let's think about an example. So what if we're going to collect some temperature data to compare it to some historical data to understand how temperature has been increasing here in New York City over the last 20 to 30 years? What might we need to just consider to make our methods more robust? Well, first of all, we need to figure out where we need to collect our temperature data. Collecting the temperature at Battery Park will produce something different than taking it in Central Park or even at Herald Square. So understanding where this other temperature data has been taken for the last 20 to 30 years can really help us to understand how our methodology should be established. Where should we be taking our temperature? Also considering, should we take the temperature in the shade or in the sun? Understanding if there is a lot of vegetation around is also extremely important. And finally, how has this location changed over the last 30 years? If the city parks has been collecting temperature data in Central Park over the last 30 years, where are they collecting it and how's that changed? Have new buildings been built around the temperature gauge? Have they put in a new pond or planted more trees? All of this will impact our results. Secondly, we need to make sure that our methods and experiment plan, all of them are replicable. through thorough documentation. Thorough documentation. Other researchers won't think that our data and our results are reliable if they can't reproduce our work. So making sure that we document is crucial, because robustness and making our results replicable only adds credibility to our results. So this is very important, very important. And then when we get our data, after we've run our experiment, we need to think about what is the quality of our data? Because poor quality put into your magical machine of analysis and results, and it spits out a result, the result will only be poor if you put in poor data. So making sure that we have good data is important. Now, good data means that often the data is unbiased, meaning we read our temperature gauge in the shade every single time we took the temperature. It is representative, meaning that the temperature was collected in the right place compared to maybe where it was taken over the last 20 to 30 years. And we have sufficient data. It means we collected it every day. We didn't have to miss a few days a week because of soccer practice. This is very important, and it goes a long way. In climate science, we actually compare our results and our data to 20 to 30 years worth of climate data to get an accurate result for the comparison. So it's very important to have sufficient data. And finally, not all data sets are going to be perfect. If you say that you're going to take your temperature every single day at, for example, 5 p.m., and you happen to show up at 4 p.m. one day and 6 p.m. the other day, I mean, it'll be close, but it won't be exactly perfect. But it's something you can work with. And this is pretty prevalent through most data. Not all data sets are perfect. So now we're going to take a look at an example temperature set. You can see on the x-axis, we have the date starting in June going through July 2020. And on the y-axis, we have temperature being read in Fahrenheit. And you can see there are kind of some weird spots on this data. So if you want to pause the video and maybe think to yourself what they might be, you can do that now. And then we'll talk about it. So now that you've had some time to think, let's give it some thought. So what might this be? It appears that there is temperature data being read in 21 degrees, 18 degrees in the middle of summer, which is quite odd and not something that happens in New York City. Why might this be? Well, it's possible that whoever was importing this data at the time put it in Celsius. And these are pretty representative numbers of 70s and 60 degree data during the summer months. The second bunch here, which is very odd, likely it wasn't 0 degrees in the middle of the summer. So maybe the person who was marking the temperature data went on vacation and they didn't happen to tell anyone that they were leaving. And so it never got recorded. Or if a machine was recording the data, maybe it broke and it took them a few days to get it fixed. And finally, this last spot here is a little interesting. It says if somebody did go on vacation, but they told their friend to continue collecting data, though their friend wasn't very astute to the collection and just estimated that each day was about 70 degrees. So understanding these problems in your data is crucial, and talking about them in your analysis will only add to the reliability of your results. So now that we have some of our results and our data collected, how do we understand it? Does it make sense? Has the temperature increased in New York City, for example? Is it a new finding? This could be a new thing in the field. What can it mean for your area of research and society? Could, for example, collecting temperature data help inform policy that could require senior citizens to have air conditioning during the summer because it's getting to be so warm? And finally, do your results match your hypothesis? And if they don't, that doesn't mean you failed. It just means you've answered a different question than what you were originally anticipating. We also have to consider correlation and causation, because this can also add some complications to our data analysis. So let's think about it. Here's an example. Here you are looking at worldwide non-commercial space launches correlating with sociology doctorate degrees awarded in the US. And you can see that between 1997 and 2009, they correlate pretty well. But does that mean there's a causation? Have the space launches impacted how many sociology degrees have been awarded, or have the number of sociology doctorate degrees awarded impacted how many space launches? I don't think so. Let's look at another one. Here is per capita consumption of chicken correlated to total US crude oil imports in the US. And I doubt that crude oil is encouraging people to eat chicken, and I doubt that eating chicken is encouraging US crude oil imports, or discouraging. So these are things that we need to take into consideration when we are trying to understand and analyze our results. And finally, how can your results be utilized? What do they mean for society? Who can use the results to make change? At the International Research Institute for Climate and Society, where I work, we believe in these 4 pillars. We generate our data. We translate our data, so that might mean translating it into a different language, like Spanish, or translating it into information that is more easily understood by the people it's being given to. Then we transfer this information to the people who will be using it, like farmers in rural Guatemala, or people who work at the weather services in Vietnam, so that they can then use the data to impact and make a difference in their community. So next is a little project we're going to do. We are going to define a hypothesis, identify who will benefit from our research and how, identify what data we need to have to conduct the project and how to get it, and figure out what tools or resources we will need for the experiment. So I have listed a few project examples here on the right, but you're welcome to pick any or create your own. But here are some ideas. They're very broad, and they're meant for you to be able to find a hypothesis or your questions, and maybe not have the same as your friend or your classmate that you are working with. So these are some ideas. Clean tap water in New York City boroughs. Oftentimes brown water can be seen coming out of faucets. There is the New York City plastic bag ban. How oil industry impacts wildlife in the US, and the impacts of rising temperatures and/or rainfall on US agriculture. So go ahead and pause and design your research project. And we will unpause when you are done with this example for 1, 2, 3, and 4. Welcome back. I hope your projects went well. Obviously, you did not need to complete the project, but follow the steps of creating part of the scientific method. So the next part we're going to discuss is communicating our results. So what makes communication effective? What can you do to communicate so that you're not going blah-de, 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 blah, and the person you're talking to isn't really interested or listening to what you're saying? Well, to start with communication, we actually have to go back several steps to some psychology. So we're going to talk a little bit about heuristics and biases. So a heuristic is a mental shortcut that allows you to make a decision, a very quick decision. And a bias is a tendency or inclination or prejudice towards or against something or someone. And biases are often learned and built over your lifetime. So let's talk about a few examples. What are some common heuristics and biases? First off is the halo effect. The halo effect is similar to what I think of, don't judge a book by its cover. Pretend that you are about to go and meet somebody you've never met before. You kind of know what they look like. You may have seen a picture of them on Facebook or on LinkedIn, and you are going to meet them. You see them walking towards you and you say, wow, they look very put together because they're in a nicely ironed suit and their hair is put back or well kept, and they are holding themselves very well. They have good posture, and they come and they give you a nice firm handshake. You probably think, well, wow, this individual, they must be very well put together. They must be very organized. They must be very smart, have a lot of education. They probably are really nice too. They're probably really nice and they probably have good morals. They're just a really great human, really great person. But you haven't even heard them speak yet. It's crazy. But you have all these preconceived ideas of this person you don't even know. And this can go in the opposite way as well. You can have a negative opinion on someone just by their appearance even. And so I think of this similar to don't judge a book by its cover. Secondly is the affinity bias. And the affinity bias states that we like to be with people who are similar to us, whether that's race, gender, people who are in the soccer club with us, people who are in the math club, people who are in band with us or in theater, right? Who are similar to us. We like to hang out with them. This is the affinity bias. Now, the anchoring bias is a bit more complicated. The anchoring bias states that an individual or person depends too heavily on an initial piece of information, or what they call an anchoring piece of information that they receive, and subsequently, thereafter, they make judgments based on this piece of information in decision making. Now, once this anchoring information is set in their mind, all future arguments, estimates, decisions, and negotiations are discussed in relation to that anchoring information. Now, this can be very difficult for us as climate scientists, because if people don't believe in climate change or in global warming, it could be very difficult to communicate our results and our findings to them. This is something that we're still dealing with today, especially in the US. And finally, the availability heuristic is also extremely important when talking about heuristics and biases. So when I talked about a heuristic earlier, I said it was a fast decision, very split second, that helps us to make a decision or come up with an answer to something. And these split second decisions are based on our experiences. The example that I like to give about the availability heuristic is that if you are going to leave your house or apartment, you know the street right outside your house, how busy it is. You know how wide the road is, and you know how long it's going to take you to get to the other side. Now, you only know this because of your experience in trying to cross the road. So in that split second, you will know if you see a car approaching, if you are going to pick your foot up off the curb and put it on the pavement to cross, or if you're going to wait. That's an availability heuristic split second decision. So how do we deal with all of this? How do we deal with people who don't hang out with us because they have a different set of friends from the affinity bias. They have preconceived ideas of us and our research because of the halo effect. They don't necessarily believe the same things that we do because of anchoring. And based on all of their previous experiences, they have just a different set of ideas and understanding than we do. How do we deal with that? How can we overcome biases? How do we overcome this to be able to communicate our research? Well, from all of the research that I've done, the conversations that I've had with other individuals, and from what I have learned, forming a connection through similarities is the most important and critical thing that you can do when trying to communicate your research. Forming a connection through what you already know about that individual, what their interests are, their hobbies, their likes. How can you communicate what you know and what your research is based on them? So, here is your final activity for this little session. You are going to take the project that you have created, though you didn't actually do the project, but based on what you learned about communication and biases and heuristics, come up with a short but well thought out proposal as to why you think your selected individual, which I'll explain in a minute, should adopt your project or results and make a change in your community. So you need to convince them to support your work. So you can choose between these 4 individuals, or you can come up with someone different, but they need to be outside of your family or friends. So for example, the first option I have here is the New York City Mayor Bill de Blasio. I also have Maine's Republican Senator Susan Collins, the New York City public figure Jimmy Fallon, and the New York City Superintendent Marisol Rosales. In the attached document by this video, you can find some information on your selected individual and a little bit of information on the heuristics and biases so that you can remember what they are. So take a few minutes and come up with a proposal based on the information that you learned about these individuals, and try to see if you can come up with a convincing argument. So pause your video here, and when you are done, you can come back into the video and we will finish. Welcome back. I hope it went well. I am sure that you all were able to convince them based on your knowledge that you have now on the scientific method improvements and on communication. So these main takeaways, so if you've been sleeping through this entire video and you woke up and you need to remember the 5 most important things, here they are. First, fulfilling a need with your research will make your work relevant. Finding who you can benefit from your research and how it will benefit society is crucial. Secondly, data quality is vital to your results and findings. Vital. Data quality is so important. So make sure when you're collecting your data, do all of your homework so that you're considering everything to make your methodology robust and replicable. Third, research must be robust and replicable, as mentioned. Fourth, utilizing your results is key to making an impact. Making sure that you are communicating your results and people are actually using them, and it's not just being written and published online. Spread the word, get people to support your research. And you need to use heuristics and biases to overcome these roadblocks, to start and make connections with others. These are the 5 most important things in my talk, and I really hope that you enjoyed all of these activities today. So thanks again for coming to the Lamont Doherty Earth Observatory open house, and hopefully we'll see you soon.